Dear viewers, welcome to our online lesson at Steve Getau 3660. I am your online teacher, Mr. Steve Getau. In our today's lesson, we shall have a great emphasis in Form 3 mathematics under one topic which poses a great challenge to learners, and that is errors and approximations. Join me in the lesson as we navigate and understand more about errors and approximations. Some of the highlights that we shall have in this topic include that we shall divide the entire topic into two portions. We shall have part 1, which we shall have it now, and part 2, which will be coming up later on. In part 1, what shall we look at? We shall look at sources of errors. We shall look at how we undertake addition and compute an error during addition and consequently during subtraction. We shall also look at multiplication, that is errors in multiplication of numbers, how errors are propagated during multiplication, and also how errors are propagated during division. Join me to the end as we look at various examples in each of these sections. Once more, I would like to thank you for having joined me in the series of the lessons that we have been having, and kindly share the video, subscribe, and comment so that we may grow the channel. Straight away, let's look at sources of errors. Sources of errors. Now, that question, where do errors arise from, will be the answer to the definition of what is an error and what we mean by approximation. Usually, when a number is approximated, there creates a difference between the true value and the approximated value, and that serves as the error of that number. So, what are, straight away we can put that down. Number 1, an error is the difference between the true value and the approximated value. Normally, you may approximate a value and it becomes slightly bigger than the original number. That difference is the error. Now, that is the basic understanding of the word error. We shall look at other versions or other areas whereby errors originate from. With that, we look at number 2, sources of errors. Sources of errors. When we get to have the so-called differences between approximated and the true value, number 1 is when we are required to state A, or Roman 1, when we are stating a number, to maybe the nearest whole number, stating a number to the nearest whole number. At times, we are required to state a certain number to the nearest whole number. For example, you're given 98. State it to its nearest whole number, which is 100. The 100 is an approximated value. There is an error of 2 in that kind of a case. Number 2, at times when we are rounding off 2, when we are rounding off a number to some stated significant figures or decimal places. Very, very important. When we are given a particular number, let us say we look at an example, a very simple example. Um, we may be told round off, we may be given a question like that one. Round off 8.7356 to four significant figures. Round off these to four significant figures. That will be approximately 1, 2, 3, 4. We check on the fifth one. It is more than 5. So that leads us to increase the fourth digit by 1. And that comes to be 9.736. You realize the rounded off value is higher than the original or the true value. That difference is an error. Or if you are told to round off to 2 decimal places, that would be 9 points. The first decimal place is 7. The second decimal place is 3. So we check on the third, and it's a 5. That leads us to rounding off to 9.74. When this number is rounded off to 2 decimal places, we get 9.74. That creates a difference between the true value and the new value. That is the kind of thing we are talking about here. In number 3, we may have an error due to truncation. When a number is truncated, truncation. When we have truncation to some maybe significant figures. Take for example, we can do an example here. Truncate 7.32792 to two significant figures, you'll find that will be approximately equal to 7.3, and we stop at that. Truncation means you chop off after the significant figures given. This is the first significant figure, this is the second one. So when we are told to truncate, that means you chop off at that point, and we get 7.3. That is to 2 significant figures. And that creates a difference between the actual and the truncated value. So truncation, there we chop off. And maybe number 4, this is the part that maybe we shall have a great focus on, and that is during recording of measurements. To some given accuracy. Recording of some measurements to some given accuracy. For example, in science and in various other areas, we may have a measurement which is length. Example, a length is recorded as 2.30 centimeters and another 2.3 centimeters. You realize that these two recordings of some measurement, the moment you see centimeters, it means that is a measurement of some given dimension somewhere. 2.30 is different in terms of accuracy from 2.3. The meaning is that after this, the next reading will be at 2.31. Next reading is 2.31. Whereas this one shows that the next reading is going to be at 2.4 because the accuracies are different, and we shall have a greater understanding in our next item that we are going to discuss here. So I would like us to look at some examples which will be drawn from the discussion that we have had here. And let us look at example 1. Example 1. We look at example 1. In our example 1, we are going to look at error due to rounding off, and we are going to see this one in terms of percentage error. Item number 1 is the figure or the number 792 is rounded off to the nearest 100. Find the percentage error due to this. The number 792, the number 792 is rounded off to its nearest 100. Find the percentage error in the result. Find the percentage error in the result. So this is matching an item which we had talked about in one of our discussions here. We had talked about stating a number to the nearest whole number, and here we are talking about stating it to the nearest 100 in the operation rounding off. So in this particular example, we need to have two values. The rounded off value is equal to, the nearest to this is 800, because in 792 we are past the 50 mark here. That means we have the error. The error due to rounding off will be 800 minus 792, and that gives us an 8. So the percentage error is equal to, this is given by error over true value, the error over true value times 100. And that we are talking about 8 over 792 times 100. The result of which we should give to at least, four significant figures. Let's get our calculator and punch in that, and in a short while get to have that value. Viewers, punch in and give. Let's have you working out what is that two figures. I believe you have approximately 1.01, and this is recurring. And to four significant figures, we shall have 1, 2, 3, 4, and we can give this to a higher value, 5 significant figures. We can give it to 5 significant figures. All right. Let's move on to question number 2. Supposing we are given, let's make this one A and this one B. We are required to round off 79.68 to two significant figures, and determine the percentage error. Determine the percentage error in the result, in that kind of an operation. So we shall talk about the rounded off result, the rounded off value coming up to be to two significant figures. Viewers, this is the first significant figure. So 1, 2. We check on the third one. It is more than 5. So this becomes 80. And we are careful, we don't say 80.0. It is just 80. Now, what is the error margin? How much is the error? That gives us 80 minus 79.68. Once more, viewers, compute that, 80 subtract that, and I want to believe that we have 0.32. So straight away, percentage error gives you 0.32 over the true value, which is 79.68 multiplied by 100, and that in percentage form gives us 0.4016. 0.40, and we are giving this to 4 significant figures as the acceptable minimum level of accuracy for our questions. Now, in part 2, although not for the entire topic, but for this lesson, we are going to look at a very important area, the fourth part in our definition here, that is when we have the source of error being measurements. Errors due to measurements. This part, you'll find that it is slightly different from the first 3 in the sense that the measurements have an attachment of to what accuracy was that done. So we move on to part 2, errors in measurements. In measurements, we have 3 forms of errors. Let's see, so we say forms of errors. We have the errors that we meet under measurements come in 3 forms. The first one is what we call Roman 1, the absolute error. Absolute error. In a particular measurement, we also have relative error. Relative error. And we also have, from these 2, the percentage error. The percentage error. So this is very, very important in the sense that we are able to note that when we talk about measurements, that is when we have length, we have width, we have values like area, volume, and so on. How were these measurements done? To what accuracy were they done? That generates absolute error and so on. Now, let's look at how do we get the absolute error. Absolute error in a measurement. The absolute error in a measurement is obtained by taking the maximum value minus the minimum value of that measurement, and then you divide that by 2. Now, how do we go about this? We shall come to some illustrations for each of them. Let's look at part B. What about relative error? So we can take this time to show the formulas. Relative error is obtained by having the absolute error all over the true value multiplied by 100. And finally, in part C, percentage error, in relative error, we have absolute error over true value, but in percentage error, we have the relative error times 100. That is this portion here times 100. And that takes us to an area whereby we shall show this one practically. What is this that we are calling the maximum value and minimum value? So let's look at example number 2 in this under these errors due to measurement. We are going to focus on some plain figures like rectangles and so on. And in this one, we need to notice that the 4 operations, that is addition, subtraction, multiplication, and division, all of them have their 3 forms of errors from in different angles. Let's look at example number 1 under this form. Example 1. We are given that a rectangle measures 2.3 centimeters by 4 centimeters. Find part 1. We are required to find its maximum, minimum, and true perimeter. And then from there, we look at B, the absolute, that is the relative error. Before we come to relative error, let's look at absolute error in its perimeter. And therefore, number C, the relative error in its perimeter. And lastly, we shall be able to look at the percentage error in its perimeter. So viewers, this is a very good question to help us digest on what we are actually referring to. We are referring to these scenarios here. And in part 1, the maximum, minimum, and true, we shall be able to generate the maximum, the minimum, and the true value. And with that, we are going to obtain an absolute error. I would like us to note here a very important item. Actually, 2 important areas, that these are errors that will arise due to some measurement. All right. After that, how are the measurements? The measurements are shown as 2.3 and the other one is shown as 4. You will notice that in 2.3, the accuracy is a 0.1, and in 4, the accuracy is a whole 1. That means the next measurement after 2.3 is a 2.4. After 2.3, the measuring unit reads 2.4. But this instrument used to measure this one suggests that the next reading is a 5. It has a whole 1 unit as its accuracy. Very good. Now, when we are having measurements, we are going to demonstrate this by having a sketch. Let us put the sketch of this diagram as shown. We have 2.3 and the longer side 4. So this is 2.3. This is the true value. And here the true value is 4 centimeters. Now, if going by this, we need to realize that the measurement actual, when it is 2.3, the accuracy to which it is done is a 0.1. And therefore, the absolute error in this individual measurement, 2.3, is a half of the accuracy. A half of the accuracy. In an individual measurement, the absolute error is calculated as half the accuracy. And that way, it is going to be a half by 0.1, and that gives you plus or minus 0.05. That means this measurement can either be higher by 0.05 or can either be lower by 0.05. That means we can, because we have space here, we can show the situation here. When the actual is 4, it means the accuracy is 1. Absolute error of this measurement is therefore a half of 1, and that is a 0.5. With that, we are going to create a table here. Very, very important. We create a table which will show the minimum, the maximum, and the true values of this measurement. So we can create a table for these two values. In this, we have the first, the second, and the third item here. In the first case, let us put in the middle here the true value. The true value. So we shall have the two measurements. The two measurements will be shown here. So that the true value, we can have the minimum here, minimum value, and the maximum possible value. If I start with 4, that is the true value. The minimum possible is obtained by us taking the absolute error plus or minus 5. For the minimum, it is 4 minus 0.5. That is 4 minus 0.5. And that gives us a 3.5. For the maximum, it is 4 plus the 0.5, and that gives us 4.5. So that is gotten from the absolute error due to this individual measurement. Let's move on to the second one. When the measurement is 2.3, let me use black, 2.3, so we have the absolute error for this measurement being that is plus or minus 0.5. For the maximum, we add 0.05. I can do it here. 2.3 add 0.05, and we get 2.35. For the minimum possible dimension here, we shall have 2.3 subtract 0.05, and that gives us, we can put a 0 here, we borrow 1 from 3, and that gives us a 5, We are left with 2, and that comes to be 2 here, and 2.25. That is 2.25. If we transfer these measurements, they will look like this. 2.25 is the minimum. The maximum is 2.35. Whereas here, the minimum is 3.5. That is minimum. The maximum is 4.5. So these measurements are going to be very, very useful as we work out the other portions there. Now, the question that we are answering is about perimeter. Perimeter. So we are going to look at the length added to the width, I beg your pardon, the length added to the width multiplied by 2. That is how we get perimeter of an object like this one. That means we may start with maximum perimeter. Here, we may start with maximum perimeter. The maximum perimeter will be obtained from twice the maximum lengths and the widths. Maximum length and maximum width. This is 2.35 is the maximum on that length, and the maximum along this direction is 4.5. Viewers, from your calculation, let us have this one as twice 6.85, and that gives us a value 13.70. What about the minimum perimeter? We obtain this one from the minimums of each of the two. So twice we select on the minimum. Here the minimum is 0.5. The minimum here is 2.25. So 2.25 plus 3.5 gives us twice. We add the values in the mid row to 5.75. And then multiplying that by 2 gives us 11.50. Now, with that, we are able to get, as we had put earlier, the absolute error. In that measurement called perimeter, we shall need the maximum minus the minimum, we divide by 2. So we have a measurement which we require called perimeter, and we've calculated it. So we shall take the 2 divided by 2. Viewers, we are not talking about the absolute error of one measurement. The measurement in the question is the perimeter. The perimeter, that is part 2. So we have already done part 1, except maybe the true perimeter. We can work on the true perimeter and then we move on to absolute error in the perimeter, not in the individual measurements. We have already cleared that. So let's look at the final part, true perimeter, so that we move to that part. So we have true perimeter. The true perimeter is the actual perimeter twice 2.3 plus 4, and that gives us twice 6.3, and that comes to be 12.6 centimeters. All these measurements are in centimeters. So this is what we are actually talking about. Part A has been done. The maximum, minimum, and true perimeters are all shown here. So that we can move to part B, whereby we shall talk about absolute error in what? In the perimeters. In the perimeter. This is from the formula maximum perimeter, which is 13.7 minus the minimum possible 11.50. The result we divide by 2, and that gives us the values 2.2 divided by 2. 2.2 divided by 2, and that gives us 1.1 as the absolute error. So the part C, relative error in the perimeter, will be obtained from the absolute error 1.1 all over the true value. The true value, we found it to be here, 12.6. And we compute that, and if possible, express it as a fraction. If you have to express it in decimal form, give it to 4 significant figures. On my part, I'm getting 0.08, 0.08, 702. 0.08702 to some 1, 2, 3, 4, 4 significant figures. And that actually takes us to the last item. The last item, I can get it some space here, whereby we look at percentage error in part D. Part D of this question, percentage error will be the relative error obtained here, 0.08702. We multiply that by 100, and that gives us 8.702, and that is a percentage which we are still giving to 4 significant figures. So viewers, the way we have done the absolute error, relative error, percentage error in perimeter signifies what we should do whenever we are adding numbers. And very important, I would like you to realize the way absolute error features in 2 ways: in an individual measurement and in a computation which is requiring addition. In the computation which requires maybe addition, to obtain the absolute error, we always go for maximum minus the minimum divided by 2. This formula will apply whether we are dividing or in dividing, subtraction, addition, and multiplication. So this particular formula is general for a measurement that is, say, area, that is multiplication. Whenever we are dividing, we shall need the same formula. Whenever we are subtracting, and so on. For all the 4 operations, addition, subtraction, multiplication, and division, these 3 formulas will apply. And we are saying an individual measurement will have its own absolute error before we transfer that to the particular measurement, like perimeter or area that we are calculating. Next, we look at a question that deals with errors in division. Let's look at example number 2. In example number 2, we look at a right-angled triangle has the dimensions of its sides given as 3, we have 4, we have 5. Viewers, these measurements are deliberately shown in different accuracies. Here, to an accuracy of 0.1. This is to an accuracy of 1, and here to an accuracy of 0.01. So what we are going to do is we can show this particular triangle. I draw a big one, and we give, this is a right-angled triangle, we give the dimensions in different colors. For instance, if I may give the colors blue, that is 3.0, we give this one at 3.0, and this one at 4, and this one at 5.00. That blue color signifies the actual. Then we look at, this time around we have gotten it, the absolute error in 3.0 is a half of 0.1, which is plus or minus 0.05. So the maximum and minimum will be 3.05. In this case, the minimum will be the subtraction of that. We subtract 0.05 from 3 and we get 2.95. So these are the dimensions for this length here. Then we move on to 4. For 4 it is relatively easier. We get the minimum to be 3.5 and the maximum to be at 4.5, and that means it's quite easy for us to get these dimensions there. In 5.00, we can compute the absolute error in 5.00 as being a half of the accuracy, 0.01, which comes to be plus or minus 0.005. That means in the maximum, it will be, I use red for the maximum, that is 5.005, and in the minimum to this, we shall have 4.995, and those will be the dimensions for the hypotenuse. That way, all dimensions are given. Ours now is to look at maximum area will therefore be a half base times height. Viewers, it is very important to notice that when we say a half, it is a constant. It does not attract any error since it is not a measurement. That goes on for constants like pi, 22/7. They will not attract any errors or any error, absolute or so, because the pi is not a measurement, it is a constant. So times, we're looking at the maximum, so we go for the maximum. 3.05 times the maximum here, 4.5. And do compute that in your calculator, and let us see what you get. 6.8625. 6.8625 centimeters squared. Now, let's look at minimum. The minimum area. The minimum area, the same, a half times the minimum, where we have the minimum. So, for this, we have 2.95. And for that height, we have 3.5. And compute that in a calculator, and let's see what we have. Myself, I have 5.1625 centimeters squared. We also need to compute true area. True area, other people call it actual area. A half times the base 3, the height 4, and that comes to be a half of 12, 6.0, or we can say 6, because the measurements did not have an accuracy greater than point something. Just 3 and 4, we give it as a 6. Straight away, therefore, we can compute these other measurements like absolute error, that is in A. Absolute error, maximum minus minimum over 2. 6.8625 minus 5.1625, we divide that by 2. And that gives us the value that we generate there, 1.7 divided by 2, and that comes to be 0.85. This is our absolute error. So you can see, the moment you are able to get this, the question is almost over. B, we have relative error. It is the absolute error, 0.85, over the true value now, 6. And where you have this, you can show it as a fraction. That is the best or the highest accuracy, or as a decimal if it is terminating. However, ours is at 1.1416, and the 6 is recurring. So I show with a dot over 6. And then in part C, we have percentage error, which is basically the relative error, 0.1416 recurring times 100. And this gives us 14.16 with the 6 still recurring is a percentage. So viewers, this is great if we are able to visualize this said. And as you can see, we said there are absolute errors in the individual measurements, which are brought here in the calculation. Our calculation is area. Area involves multiplication. And once more, we are using this golden formula about maximum area over, subtract minimum area over 2. And looking at this, if we are to award marks in this case, you'd find that calculating this as 1 mark, we can call it an M1, getting this correctly, M1, and having this also done an M1, such that in part A, you have about 3 marks, here, 3 marks here. In part 2, whereby you have this computed correctly, 1 mark, M1, and this is A1, you get 2 marks. When you compute this correctly, M1, and this accurate answer, A1, you get another 2 marks. 2 marks. And finally, when you can't compute that one, M1, and this is A1, you get around 2 marks. So this is a question that may attract, this is 2, 4, 6 plus 3, about 9 or 10 marks in ordinary working. So all these areas, and indeed, we can look at how did the student apply the knowledge of errors. If it is correctly done, M1, so that knowledge is brought here, and we can award the 10 marks in such kind of working. We give it 10 marks. It's a lengthy kind of working. Viewers, I would like us to look at the last part, and this is going to involve division. How do we get absolute error, relative error, and percentage error in dividing? That will coming up in example number 3. In example number 3, we look at find the percentage error in dividing 2.35 divided by 4. So straight away, we are going to visualize the solution. This can be shown as 2.35 divided by 4. They are measurements, centimeters by centimeters. So in this case, we are going to look at a special kind of case whereby we can show this in table form. We can show this in tabular form, whereby we look at this is plus or minus 0.0, another 0.5. This is plus or minus 0.5. The absolute errors in each measurement there. So we are going to form a table whereby we shall have the values, their maximum, and their minimums. So let's do that now. We have maximum, we have true, and we have minimum, and we have the minimum for each of these two values. Each of these two values. That will be our table for that, and we can show these two values there. Right, now the values are 2.35 and 4. Meaning, if you look at the maximum, it's going to be 2.35, and we add the 5 there, 2.35, and the minimum is 2.345. Whereas this is going to be minimum 3.5 and maximum here 4.5. Now let's look at what we call the maximum quotient. The maximum result of division, maximum quotient of a value A all over B. It's going to be obtained by having the maximum of A divided by the minimum of B. So that is the special condition in this issue of division. You have to, if you want to get a maximum after dividing, the numerator must be maximum, the denominator must be minimum. And that gives us 2.355, that one, and we go that with the minimum over 3.5, and that comes to be 471 471 all over 700 in fraction form. We look at minimum of a particular quotient, A over B. When two numbers are B divided, what do? To get that, you need the minimum of A all over the maximum of B. And that is, the minimum of A is this one, at 2.345, but you divide by the maximum of B, 4.5. And that comes to be 469 all over 700. Now, what is the true value in this case? Because we shall definitely require that. That is 2.35. The true value will be obtained by having 2.35 divided by 4, and you can compute that as a fraction. However, in our calculation, since we are talking about directly percentage error, you might find that it will not be of importance in the working. I was just putting it so that we may actually be able to know that even in division, the true value is calculated. So now let's look at absolute error. Absolute error is the maximum minus the minimum all over 2. And that gives us, from this computation, 471 all over 700, subtract 469 all over, this is 469 over 900, I beg your pardon. This is over 900, over 900. This value, we should be able to divide it by a half. So we compute that by a half, and we get 239 divided by 239 divided by 1575. We divide that by 1575. And with this, we can compute the percentage error as being equal to, we get the absolute error, that is 239 all over 1575. We divide that by what we had gotten here as the true value, that is the 2.35 divided by 4. The result of that, we multiply by 100. And on my part, I have gotten 7.5873%. So the most important area was our ability to get the maximum over division, the minimum over division. Then using the area formula, maximum minus minimum over 2, we get the absolute error. Once we get the absolute error, we are going to use absolute error over the true value of the division, then multiply the result by 100, and then we are done. Viewers, we've come to the end of our lesson, and this is not the end of the topic errors and approximations. We are going to have part 2, whereby we shall look at more questions so that we get more light and greater understanding in this particular topic. I have been your teacher, Mr. Steve Getao, and I do thank you for having joined me in this lesson. I look forward to joining you in our upcoming videos on, or rather, in Form 3 mathematics. In our next video, we shall look at matrices and the various operations under matrices. I look forward to meeting you then. Subscribe, share, and comment, and we grow the channel. Thank you.